Picture this, our entire galaxy, the Milky Way, stretching across 100,000 light-years of space, filled with hundreds of billions of stars. It feels impossibly vast, doesn't it? And yet, when we zoom out to see the true scale of the universe, our galaxy becomes so small that it almost disappears. Tonight, we're going to gently explore just how tiny our cosmic home really is. To understand this comparison, we need to start somewhere familiar. We need to begin here, on Earth, in our solar system, and slowly expand outward. Think of it like standing in your backyard and then gradually rising up higher and higher until the entire planet becomes a dot. Then we keep going. We'll move through our galaxy, past neighboring galaxies, and eventually reach scales that challenge everything we thought we knew about size and distance. Let's begin our journey. Our home galaxy is called the Milky Way. On a clear night, away from city lights, you can see a soft band of light stretching across the sky. That band is our view of the galaxy from inside it. We live within the Milky Way, about 2/3 of the way out from the center. Imagine a giant spiral, like a cosmic whirlpool made of stars, gas, and dust. That's our galaxy. It spins slowly through space, and we're just one tiny part of it. The Milky Way is about 100,000 light-years across. A light-year is the distance light travels in 1 year. Light moves incredibly fast, covering about 186,000 miles every single second. In 1 year, light travels nearly 6 trillion miles. So when we say the Milky Way is 100,000 light years wide, we're talking about a distance so large that it takes light 100,000 years to travel from one side to the other. That's hard to picture, but let's try. If you could travel at the speed of light, you could circle the Earth 7 times in just 1 second. You could reach the moon in a little over 1 second. You could reach the sun in about 8 minutes. But to cross the Milky Way, even at light speed, would take 100,000 years. That's more than twice as long as modern humans have existed on Earth. It's a journey that would span thousands of generations. Our solar system sits in one of the spiral arms of the Milky Way. These arms are like rivers of stars swirling around the galactic center. We orbit that center along with billions of other star systems, completing one full orbit every 230 million years or so. The last time we were in this exact spot in our galactic orbit, dinosaurs were just beginning to appear on Earth. Think about that for a moment. Our entire solar system is drifting through space on this incredibly long, slow journey around the galaxy. The center of the Milky Way is about 26,000 light-years away from us. At the very heart of our galaxy, there's a supermassive black hole called Sagittarius, a star. It weighs about 4 million times more than our sun. This black hole doesn't pull the entire galaxy into it because gravity from all the stars and dark matter balances things out. Instead, the black hole sits quietly at the center, anchoring the galaxy as everything else swirls around it. Between the stars, there's mostly empty space. If our sun were the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. That's how spread out things are. Even in our crowded galaxy, there's an enormous amount of emptiness. Stars are like tiny islands in a vast ocean of nothing. The Milky Way contains somewhere between 100 billion and 400 billion stars. Nobody knows the exact number because many stars are too dim to see, even with our best telescopes. Some of those stars are much bigger than our sun, some are much smaller, some are old and dying, others are brand new, just beginning their long lives. Around many of those stars, there are planets. Some of those planets might be similar to Earth, some might even have life, though we haven't found any yet. Besides stars and planets, the Milky Way contains massive clouds of gas and dust. These clouds are where new stars are born. Gravity pulls the gas and dust together, and when enough material gathers in one place, the pressure and heat become so intense that nuclear fusion begins. A star is born. This process happens all the time throughout the galaxy. Right now, as you listen to this, new stars are forming in clouds scattered across the Milky Way. There are also old stars that have reached the end of their lives. Some explode in brilliant supernovas, scattering their material back into space. That material becomes part of new clouds, which eventually form new stars and planets. It's a cycle that has been going on for billions of years. In fact, the atoms in your body were once inside ancient stars. You are made of stardust, forged in the hearts of stars that died long before our sun even existed. From our perspective on Earth, the Milky Way looks flat and stretched out across the sky. But if we could see it from above, we'd notice that it's actually a spiral with several arms. Our sun is located in a smaller arm called the Orion Arm, or sometimes the Orion Spur. It's a relatively quiet neighborhood far from the intense radiation and crowded star clusters near the galactic center. If you could somehow travel to the edge of the Milky Way and look back, you'd see a beautiful spiral galaxy glowing against the darkness of space. The center would be bright, packed with billions of old stars giving off a warm, yellowish light. The spiral arms would glow with blue light from young, hot stars. Dust lanes would create dark ribbons winding through the arms. It would be one of the most beautiful sights imaginable. But here's the thing, as vast as the Milky Way is, as impossibly large and ancient and full of wonders, it's just one galaxy. There are countless others out there, scattered throughout the universe. And compared to the true scale of everything that exists, the Milky Way is just a beginning. It's our home, yes, but it's a very small home in a neighborhood much larger than we can easily imagine. Our galaxy is ancient. It formed about 13.6 billion years ago, not long after the Big Bang. For almost the entire history of the universe, the Milky Way has been here, slowly evolving, forming new stars, swirling through space. Generations of stars have lived and died within it. Planets have formed and been destroyed. And somewhere along the way, on one small planet orbiting one ordinary star, life appeared. That life eventually evolved into us, creatures capable of looking up at the night sky and wondering about our place in it all. When you think about the Milky Way, it's easy to feel small. And you should, because you are small. We all are. But there's something beautiful about that smallness. It means we're part of something much bigger than ourselves. We're connected to the galaxy in ways we're only beginning to understand. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it came from stars. We are not separate from the cosmos. We are the cosmos looking back at itself. The Milky Way has structure that astronomers have mapped carefully over many decades. It has a central bulge, a dense region of old stars surrounding the supermassive black hole. Extending from this bulge are the spiral arms, curved lanes of stars and gas that wind outward. There's also a halo of old stars and globular clusters that orbit above and below the flat disk of the galaxy. All of these components work together, held in place by gravity, creating the complex system we call home. Understanding the structure of our galaxy took centuries of careful observation. Ancient peoples saw the Milky Way as a river of light across the sky. Some cultures thought it was a pathway for souls traveling to the afterlife. Others imagined it as spilled milk from a goddess. It wasn't until telescopes were invented that we began to understand what we were really seeing. Galileo was one of the first to point a telescope at the Milky Way. He discovered that the band of light was actually made up of countless individual stars, too faint and distant to see with the naked eye alone. This was a revelation. The Milky Way wasn't a cloud or a river. It was stars, vast numbers of them, all contributing their light to create the glow we see. Over time, astronomers realized that our sun was part of this great collection of stars. We weren't observing the Milky Way from outside, we were inside it, looking through it. This changed everything. It meant we needed to map our galaxy from within, like trying to understand the layout of a forest while standing among the trees. William Herschel, an astronomer in the late 1700s, attempted to map the Milky Way by counting stars in different directions. He concluded that the galaxy was shaped like a flat disk with the sun near the center. He was partly right about the shape, but wrong about our position. We now know the sun is nowhere near the center. We're out in the suburbs, far from the galactic downtown. The true center of the Milky Way lies in the direction of the constellation Sagittarius. From Earth, this region is obscured by dust and gas, making it hard to see in visible light. But using infrared and radio telescopes, astronomers have been able to peer through the dust and study what lies at the heart of our galaxy. That's how they discovered Sagittarius, a star, the supermassive black hole lurking there. The spiral arms of the Milky Way are regions where stars and gas are more concentrated. They're not solid structures. Stars drift in and out of the arms as they orbit the galaxy. The arms persist because they're density waves, like traffic jams that remain in the same place even as individual cars move through them. When gas clouds enter a spiral arm, they get compressed, triggering star formation. That's why the arms are bright with young, hot stars. Our Sun currently resides in what's called the Orion Arm, also known as the Orion Spur. This is a smaller arm between two major spiral arms, the Perseus Arm and the Sagittarius Arm. We're in a relatively quiet part of the galaxy, which may be fortunate for life. In the denser inner regions or in the crowded spiral arms, there's more radiation, more frequent supernovas, and more gravitational disturbances that could disrupt planetary systems. The Milky Way rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, stars orbit quickly, completing a circuit in just a few million years. Out where we are, the orbital period is much longer, about 230 million years. This difference in rotation speeds creates the spiral pattern. If the galaxy rotated like a solid disk, the spiral arms would wind up tighter and tighter over time and eventually disappear. The rotation of the galaxy also reveals something puzzling. When astronomers measured how fast stars were moving at different distances from the center, they found something unexpected. The stars were moving faster than they should be, based on the visible mass of the galaxy. There wasn't enough matter to account for the gravitational pull needed to keep stars in their orbits at those speeds. This led to the realization that most of the mass in the Milky Way and in other galaxies is invisible. It doesn't emit light or absorb light. It doesn't interact with normal matter except through gravity. Astronomers call this mysterious substance dark matter. Nobody knows what dark matter is made of, but we know it's there because we can see its gravitational effects. The Milky Way is thought to be surrounded by a massive halo of dark matter extending far beyond the visible stars. This halo could be several 100,000 light-years across, much larger than the visible galaxy. The dark matter provides the extra gravity needed to hold the galaxy together and explain the rotation speeds we observe. Besides dark matter, the galaxy also contains large amounts of gas between the stars. Most of this is hydrogen, the simplest and most abundant element in the universe. Some of it exists as cold, dark clouds. Other regions are warm and diffuse, filling the spaces between stars. And in some areas, the gas is heated to millions of degrees by supernova explosions and stellar winds, creating bubbles of hot plasma. This interstellar gas is the raw material for future generations of stars. Over time, gravity will cause some of the gas to condense into new clouds, and those clouds will collapse to form new stars and planetary systems. The cycle continues, generation after generation, ensuring that the Milky Way remains a vibrant, star-forming galaxy. The galaxy also contains dust, tiny particles of carbon, silicon, and other elements. This dust scatters and absorbs light, creating the dark lanes we see in images of the Milky Way. Dust might seem like a nuisance, blocking our view of distant stars, but it's essential for planet formation. Rocky planets like Earth are made from dust particles that clump together in the early solar system. Throughout the Milky Way, there are stellar remnants, the leftovers from stars that have died. Some are white dwarfs, the cooling cores of sun-like stars that have shed their outer layers. Others are neutron stars, incredibly dense objects formed in supernova explosions. A teaspoon of neutron star material would weigh billions of tons. And scattered throughout the galaxy are black holes, regions where gravity has become so strong that nothing can escape, not even light. Black holes come in different sizes. Stellar mass black holes form when massive stars die. They're typically a few times more massive than the Sun. But there are also supermassive black holes, millions or billions of times more massive, found at the centers of galaxies. Our galaxy's central black hole, Sagittarius, a star, is relatively quiet. It's not actively consuming large amounts of material, but other galaxies have more active black holes that shine brilliantly as matter spirals into them. The Milky Way has satellite galaxies, smaller galaxies that orbit around it. The Magellanic Clouds are the most famous, visible from the southern hemisphere. But there are many others, most of them faint, dwarf galaxies containing only a few million stars. Some of these satellites are being slowly torn apart by the Milky Way's gravity, their stars streaming out in long tails. Over billions of years, these stars will be absorbed into the Milky Way, making our galaxy slightly larger. The galaxy has a complex history. It formed from a cloud of gas about 13.6 billion years ago, not long after the Big Bang. The first stars were different from stars today. They contained almost no elements heavier than hydrogen and helium. because those heavier elements hadn't been created yet. Only after those first stars died and scattered their enriched material did later generations of stars form with the elements necessary for rocky planets and life. Over billions of years, the Milky Way grew through mergers with smaller galaxies. Each time a small galaxy was absorbed, its stars were added to our galaxy. This process is ongoing. The Milky Way is still consuming smaller galaxies today. In fact, we can see streams of stars in our galaxy's halo that came from ancient mergers, the remnants of galaxies that no longer exist. The Milky Way will continue to evolve. In a few billion years, it will merge with the Andromeda Galaxy, creating a new, larger galaxy. This merger will dramatically change both galaxies. The spiral structures will be disrupted, stars will be flung into new orbits, and new waves of star formation will ignite as gas clouds collide. Eventually, the combined galaxy will settle into a new shape, probably an elliptical galaxy rather than a spiral. But that's far in the future. For now, the Milky Way is a magnificent spiral galaxy filled with stars, gas, dust, and mystery. It's a place where new stars are constantly being born and old stars are dying. It's a place where planets orbit suns, where comets streak through space, where nebulae glow with ethereal colors. It's a place of incredible beauty and wonder, and it's our home. Every human who has ever lived was born in this galaxy. Every civilization that has risen and fallen did so under these stars. Every dream, every achievement, every moment of joy and sorrow, all of it happened here, in the Milky Way. That connection makes our galaxy special, regardless of how small it might be in the larger universe. Stars in the Milky Way come in many different types. Red dwarfs are the most common, small and cool, burning their fuel slowly over trillions of years. Yellow stars like our Sun are medium-sized and middle-aged, stable and warm. Blue giants are massive and hot, burning bright but dying young in spectacular explosions. White dwarfs are the cooling remnants of dead stars, no longer fusing elements but still glowing with leftover heat. Neutron stars are the crushed cores of exploded stars, incredibly dense and spinning rapidly. And black holes are regions where gravity has become so strong that nothing, not even light, can escape. The variety of stars in our galaxy is remarkable. No two stars are exactly alike, just as no two snowflakes are identical. Each star has its own mass, temperature, composition, and age. Some stars are solitary like our Sun, but many exist in binary or multiple star systems where 2, 3, or even more stars orbit each other. Binary stars are particularly interesting. In close binary systems, the stars can exchange mass. Material flows from one star to the other, creating spectacular displays of energy. Sometimes this mass transfer can trigger nova explosions, where the surface of a white dwarf suddenly ignites in a thermonuclear blast. These novas can briefly shine as brightly as an entire galaxy before fading back to normal. Some binary systems contain a compact object like a neutron star or black hole paired with a normal star. As the normal star loses material to its compact companion, the infalling gas heats up and emits intense X-rays. These X-ray binaries are among the brightest X-ray sources in the sky. They provide laboratories for studying extreme physics, testing Einstein's theories under conditions we could never reproduce on Earth. The life cycle of stars is one of the most beautiful stories in astronomy. Stars are born in cold, dark clouds of gas and dust. Gravity slowly pulls the cloud together, and as it shrinks, the center heats up. Eventually, the temperature and pressure become high enough for nuclear fusion to begin. Hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy. This energy creates pressure that balances gravity, and the star enters a long, stable period burning hydrogen in its core. For stars like our Sun, this stable period lasts about 10 billion years. More massive stars burn their fuel faster and live shorter lives, some lasting only a few million years. Less massive stars burn more slowly and can live for trillions of years, longer than the current age of the universe. The smallest red dwarfs that formed in the early universe are still on their first generation of hydrogen burning, and they'll continue for trillions of years to come. When a star exhausts the hydrogen in its core, its fate depends on its mass. Stars like the Sun will swell into red giants, fusing helium in their cores and hydrogen in a shell around the core. Eventually, they'll shed their outer layers, creating beautiful planetary nebulae, and leave behind a white dwarf core that slowly cools over billions of years. More massive stars have more dramatic endings. They can fuse progressively heavier elements, building up a core of iron. But iron can't be fused to release energy. Instead, fusing iron requires energy. So when a massive star builds up an iron core, fusion stops, pressure drops, and the core collapses catastrophically. In less than a second, the core implodes and then rebounds in a supernova explosion so powerful it can briefly outshine an entire galaxy. These supernovas are crucial for the galaxy's chemical evolution. They create and disperse heavy elements, enriching the interstellar medium with the building blocks of planets and life. Without supernovas, there would be no carbon, no oxygen, no iron, none of the elements necessary for rocky planets and biological molecules. We owe our existence to stellar explosions that occurred billions of years ago, events so violent they tore stars apart, but so generative they seeded space with the materials of future worlds. The remnants of supernovas are also fascinating. Some leave behind neutron stars, objects so dense that a teaspoon of their material would weigh 1 billion tons on Earth. Neutron stars are only about 20 kilometers across, the size of a city, but they contain more mass than the Sun. They spin rapidly, sometimes hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. Some neutron stars are pulsars, emitting beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. Beams. If Earth happens to be in the path of one of these beams, we detect regular pulses of radio waves, hence the name pulsar. The first pulsar was discovered in 1967, and for a brief time astronomers wondered if they might be artificial signals from an alien civilization. They're not, of course, but they remain some of the most precise clocks in the universe. Other supernova remnants become black holes, regions where gravity has crushed matter to infinite density in an infinitely small point, at least according to our current theories. Near a black hole, space and time behave in strange ways. Time slows down, space is warped, and beyond a certain boundary called the event horizon, even light cannot escape. Black holes are invisible, but we can detect them by their effects on surrounding matter and space. The Milky Way contains millions of stellar mass black holes, the remnants of massive stars. Most are quiet and isolated, invisible against the darkness of space. But some are in binary systems, pulling matter from companion stars. As this matter spirals into the black hole, it heats up and emits X-rays, betraying the black hole's presence. And then there's Sagittarius A star, the supermassive black hole at the galaxy's center. It's 4 million times more massive than the Sun, yet remarkably quiet. It doesn't consume much material. Stars orbit it at incredible speeds, their motion revealing the black hole's immense gravitational pull. By tracking these stars over years and decades, astronomers have confirmed that a massive compact object, almost certainly a black hole, sits at the exact center of our galaxy. In 2022, astronomers released the first image of Sagittarius, a star captured by the Event Horizon Telescope. It shows a glowing ring of hot gas surrounding a dark center, the shadow of the black hole itself. This image, years in the making and requiring the coordination of telescopes around the world, confirmed what had long been suspected. Our galaxy's heart harbors one of the universe's most extreme objects. Each type of star plays a role in the galactic ecosystem. Massive stars live fast and die young, exploding as supernovas and spreading heavy elements into space. These elements become part of the next generation of stars and planets. Without this recycling process, there would be no rocky planets like Earth, and no elements necessary for life as we know it. The Milky Way is not just a collection of stars, it's a living, evolving system where matter constantly changes form. The disk of the Milky Way is relatively thin compared to its width. If the galaxy were the size of a pancake, it would be thinner than the pancake. Most of the stars, gas, and dust are concentrated in this flat disk, which is why we see the Milky Way as a band across our sky. We're looking through the disk from inside it. When we look perpendicular to the disk, out of the plane of the galaxy, we see far fewer stars. The sky appears darker in those directions. The Milky Way also contains dark matter, a mysterious substance that doesn't emit light or interact with regular matter except through gravity. Scientists know dark matter exists because galaxies rotate in ways that only make sense if there's much more mass present than we can see. In fact, Dark matter outweighs regular matter by about 5 to 1. The Milky Way is embedded in a massive halo of dark matter that extends far beyond the visible stars. This dark matter helps hold the galaxy together and influences how it moves through space. Within the Milky Way, there are regions called nebulae, vast clouds of gas and dust illuminated by nearby stars. Some nebulae glow with beautiful colors, red from hydrogen, blue from oxygen, green from other elements. These are stellar nurseries, places where stars are actively forming. The Orion Nebula, visible to the naked eye, is one such region. Inside it, thousands of stars are being born right now, condensing out of the swirling gas and dust. Other nebulae are the remnants of dead stars. When a massive star explodes, it leaves behind an expanding shell of gas called a supernova remnant. These shells can persist for thousands of years, gradually mixing with the surrounding interstellar medium. The Crab Nebula is a famous example, the leftover debris from a supernova that was observed on Earth in the year 1054. Our galaxy also contains binary star systems, where two stars orbit each other bound by gravity. Some of these systems are so close that material flows from one star to the other, creating dramatic flares and eruptions. Other binaries are wide, with the stars separated by distances comparable to the size of our solar system. Many stars, perhaps most, are part of multiple star systems rather than being solitary like our Sun. There are also star clusters within the Milky Way. Open clusters contain a few hundred to a few thousand young stars, all born from the same cloud of gas. These clusters gradually disperse over time as their stars drift apart. Globular clusters, on the other hand, are ancient and tightly packed, containing hundreds of thousands of old stars in a spherical shape. The Milky Way has about 150 known globular clusters, most of them orbiting in the halo above and below the galactic disk. The Milky Way is not static, it's constantly changing, evolving over time. New stars are born, old stars die, gas flows in patterns throughout the disk, and the spiral arms slowly shift their shape. The galaxy is also moving through space, orbiting within larger structures that we'll explore soon. Everything is in motion, nothing stays the same. The galaxy you see tonight is slightly different from the galaxy that existed 1,000 years ago, and it will be different again in another 1,000 years. So as we prepare to zoom out and see the Milky Way from a larger perspective, remember this: our galaxy is home. It's where we come from. It's where our story begins. And even as we discover how small it is compared to everything else, it remains special. Because it's ours. It's the place where we were born, where we live, where we first learned to look up at the stars and ask questions. Now let's step outside our galaxy and see what else is out there. The Milky Way doesn't exist alone, it has neighbors. If you could step far enough away from our galaxy to see it as a whole, you'd notice other galaxies nearby. Some are large, like ours, others are much smaller. Together, they form what astronomers call the local group. The local group is a collection of more than 50 galaxies bound together by gravity. They orbit around a common center, slowly dancing through space. The Milky Way is one of the largest members of this group, but it's not the biggest. That honor goes to the Andromeda Galaxy, also known as M31. Andromeda is about 2.5 million light-years away from us. That might sound like an enormous distance, and it is. But on the scale of the universe, Andromeda is practically next door. It's our closest large galactic neighbor. If you know where to look, you can actually see Andromeda with your naked eye on a dark night. It appears as a faint, fuzzy patch of light. When you look at that patch, you're seeing light that left Andromeda 2.5 million years ago, long before modern humans existed. Time Neocroins, Beker Andwalferdam. Andromeda is a bit larger than the Milky Way. It contains roughly 1 trillion stars compared to our few hundred billion. It's also a spiral galaxy, similar in shape to ours. If you could see both galaxies from the same angle, they'd look like twins. Andromeda has its own spiral arms, its own clouds of gas and dust, and its own supermassive black hole at the center. Here's something interesting. Andromeda is moving toward us. The two galaxies are on a collision course drawn together by gravity. In about 4 billion years, the Milky Way and Andromeda will merge. It sounds violent, but it will actually be a slow, graceful process. The galaxies will pass through each other, their stars swirling and mixing. Because there's so much empty space between stars, actual collisions will be rare. Most stars will simply find new orbits in the combined galaxy. When the merger is complete, the Milky Way and Andromeda will form a single, giant elliptical galaxy. Astronomers have already given it a name, Milkomeda. By that time, our sun will be nearing the end of its life. Earth might not even be habitable anymore. But if any of our distant descendants are still around, they'll have a spectacular view of the night sky as the two galaxies blend together. Besides Andromeda, the local group contains many smaller galaxies. Two of the most notable are the Large Magellanic Cloud and the Small Magellanic Cloud. These are dwarf galaxies that orbit the Milky Way. From the southern hemisphere of Earth, they look like detached pieces of the Milky Way, glowing softly in the night sky. The Large Magellanic Cloud is about 160,000 light-years away. It contains roughly 30 billion stars. That might sound like a lot, but it's a fraction of what the Milky Way holds. The Large Magellanic Cloud is irregular in shape, not a neat spiral like our galaxy. It's thought to be slowly being torn apart by the Milky Way's gravity. In a few billion years, it might be absorbed entirely, its stars becoming part of our galaxy. The Small Magellanic Cloud is even smaller and farther away, about 200,000 light-years from us. It contains only a few billion stars. Like its larger companion, it's also being pulled apart by the Milky Way. These two dwarf galaxies are like satellites, orbiting our galaxy and slowly spiraling inward. There are many other dwarf galaxies in the local group. Most are so faint that they're hard to see. Even with powerful telescopes, some were only discovered in the last few decades. Each one is a small collection of stars, quietly existing in the space between the larger galaxies. Some dwarf galaxies are spherical in shape, others are irregular and chaotic. The local group as a whole spans about 10 million light-years across. To put that in perspective, the Milky Way is only 100,000 light-years wide. The local group is 100 times larger than our galaxy. Suddenly, the Milky Way doesn't seem quite so big anymore. It's just one member of a small cosmic neighborhood, a neighborhood that's itself just a tiny part of something much larger. Gravity holds the local group together. All the galaxies within it are gravitationally bound, meaning they'll never drift apart. They'll continue to orbit each other, occasionally colliding and merging, slowly transforming over billions of years. The local group is not static, it's a dynamic, evolving system. When we look at the local group, we start to see a pattern. Galaxies aren't scattered randomly through space. They cluster together, drawn by gravity into groups and larger structures. The local group is just one of countless galaxy groups scattered throughout the universe. And those groups, in turn, are part of even larger structures. The galaxies in the local group have been interacting for billions of years. Their gravitational pulls affect each other's shapes and orbits. Some galaxies have been distorted by close encounters, their stars pulled into long streams and tails. Others have captured smaller galaxies, absorbing them over time. This process of galactic cannibalism is common. Large galaxies grow by consuming smaller ones. Each galaxy in the local group has its own character and history. The Triangulum galaxy, also known as M33, is the third largest member after Andromeda and the Milky Way. It's a beautiful spiral galaxy about 3 million light-years away, slightly farther than Andromeda. Triangulum contains roughly 40 billion stars, making it smaller than either of its large neighbors. It might be a satellite of Andromeda, gravitationally bound to that giant galaxy. Some astronomers believe Triangulum might have passed close to Andromeda in the past, with their gravitational interaction creating distortions in both galaxies. The future of Triangulum is uncertain. It might be absorbed by Andromeda before the Andromeda-Milky Way merger, or it might survive to become part of the eventual three-way collision that creates Milkomeda. The dwarf galaxies in the local group are fascinating in their own right. They're much smaller than the major spirals, but they still contain millions of stars. Some are spherical, like miniature elliptical galaxies. Others are irregular, lacking any clear structure. Many of these dwarfs are satellites of larger galaxies, trapped in orbit by their more massive neighbors. The Sagittarius dwarf elliptical galaxy is particularly interesting. It's currently passing through the disk of the Milky Way, being torn apart by tidal forces. Streams of stars from this dwarf galaxy have been found wrapping around the Milky Way, evidence of its gradual destruction. In a few billion years, it will be completely absorbed, its stars becoming indistinguishable from those born in the Milky Way itself. Other notable dwarf galaxies include the Fornax dwarf, the Sculptor dwarf, and the Sextans dwarf. These are all satellites of the Milky Way, orbiting in the halo above and below the galactic disk. They're ancient galaxies, some nearly as old as the universe itself. Studying them helps astronomers understand how galaxies formed and evolved in the early universe. The Large Magellanic Cloud has its own satellites, even smaller dwarf galaxies that orbit it. This is remarkable. A dwarf galaxy orbiting the Milky Way has its own satellites, its galaxies all the way down, layers of gravitational hierarchy extending from the largest structures to the smallest. The interaction between galaxies in the local group is not always destructive. Sometimes close encounters can trigger bursts of star formation. When two galaxies pass near each other, their gas clouds can be compressed, causing stars to form more rapidly than usual. This creates regions of intense blue light from young, hot stars. The colliding gas and dust also glow brightly in infrared light, heated by the newborn stars within. The local group is isolated from other galaxy groups by vast stretches of empty space. The nearest significant galaxy group is the Sculptor group, about 11 million light-years away. Beyond that is the Milky group, and farther still are other groups and clusters. These neighboring groups are all part of the larger cosmic structure, but they're separated by distances so large that their gravitational influence on each other is minimal. Within the local group, gravity dominates. The galaxies are bound together, their fates linked. They'll continue to interact, merge, and evolve together over cosmic time. The local group of the future will look very different from the local group of today. Some of the dwarf galaxies will be absorbed by larger ones. The major spirals will eventually merge. The configuration of galaxies will change, but they'll remain gravitationally connected. The motion of galaxies within the local group is complex. They're not simply orbiting a common center. Instead, each galaxy follows its own path, influenced by the gravitational pull of all the others. Some are moving toward us, like Andromeda. Others are moving away or sideways across our line of sight. Tracking these motions helps astronomers understand the distribution of mass in the group, including the unseen dark matter. The local group has a total mass estimated at about 2 trillion times the mass of the Sun. Most of this mass is dark matter, invisible except through its gravitational effects. The visible stars, gas, and dust account for only a small fraction of the total. This is true for galaxy groups throughout the universe. Dark matter outweighs normal matter by a factor of 5, or 6 to 1. The age of galaxies in the local group varies. Some of the dwarf galaxies are very old, formed in the early universe when conditions were different. The major spirals like the Milky Way and Andromeda have been growing and evolving for most of cosmic history, accumulating mass through mergers and gas accretion. They're still forming stars today, though at a slower rate than in their youth. The study of the local group is important for understanding galaxies in general. Because these galaxies are relatively close, we can study them in great detail. We can resolve individual stars, map their gas clouds, and trace their dark matter halos. This level of detail isn't possible for more distant galaxies. The local group serves as a laboratory for testing theories about how galaxies form, evolve, and interact. Astronomers have discovered that the local group is moving as a whole through space. We're being pulled by the gravity of a massive concentration of galaxies in the direction of the Virgo cluster. This motion is separate from the expansion of the universe. While space itself is expanding, carrying distant galaxy groups away from us, the local group is simultaneously drifting toward Virgo, pulled by gravity. The local group also participates in larger-scale motions. We're part of a flow of galaxies moving toward the Great Attractor and the Shapley Supercluster beyond it. These motions are slow by human standards, but over millions and billions of years, they carry galaxy groups across vast distances through the cosmos. The environment of the local group is relatively quiet compared to some regions of the universe. We're not in a dense galaxy cluster, where collisions and interactions are frequent. We're in a small group in a relatively empty region of space. This may be significant for life. In denser environments, there's more radiation, more gravitational disturbances, and potentially more threats to developing civilizations. The future of the local group is tied to the larger cosmic story. As the universe continues to expand, the local group will remain gravitationally bound while other structures move farther away. Eventually, billions of years from now, the local group will have merged into a single large galaxy. that galaxy will find itself increasingly isolated as other groups and clusters recede beyond the cosmic horizon. But for now, the local group is a vibrant collection of galaxies, each with its own story to tell. From the massive spirals to the tiny dwarfs, from the star-forming regions to the ancient globular clusters, there's incredible diversity packed into this small corner of the universe. And somewhere within it, in one unremarkable spiral arm of one medium-sized galaxy, is Earth, our homeworld. Within the local group, most of the mass is concentrated in the Milky Way and Andromeda. Together, these two large spirals dominate the group. The other galaxies are much smaller, mere satellites compared to the two giants. But even the smallest dwarf galaxy contains millions of stars, each one a sun in its own right. If we zoom out further, the local group becomes just a small dot in our view. And that's when things start to get truly mind-bending, because the local group, vast as it is just the beginning. It's part of a much larger cosmic web, a structure so immense that the Milky Way becomes almost invisible within it. But before we take that next step outward, let's pause for a moment and appreciate what we've learned. The Milky Way is huge, containing hundreds of billions of stars and stretching 100,000 light-years across. But it's just one galaxy in a group of more than 50. That group spans 10 million light-years, a distance so large that light from one side takes 10 million years to reach the other side. And yet, we're only just beginning to see the true scale. The local group is small compared to what comes next. It's a single neighborhood in a vast city, a single tree in an immense forest. As we continue our journey outward, the Milky Way will shrink further and further, becoming smaller and less significant with each step. This isn't meant to be depressing, it's meant to be humbling. It's a reminder that we're part of something unimaginably vast. Our lives, our planet, our entire galaxy, they're all threads in a cosmic tapestry that extends far beyond what we can see. And the more we learn about that tapestry, the more beautiful and mysterious it becomes. So let's keep going. Let's zoom out even further and see what lies beyond the local group. Now we're going to scale up significantly. We've left the local group behind, and as we continue to zoom out, we begin to see something incredible. Galaxies aren't just grouped into small clusters, they're organized into much larger structures called superclusters. And the Milky Way, along with the entire local group, is part of one of these superclusters. It's called Laniakea. The name Laniakea comes from Hawaiian and means immeasurable heaven. It's a fitting name for something so vast. Laniakea is a supercluster of galaxies, a collection of galaxy groups and clusters all gravitationally connected. It's like a continent of galaxies floating in the cosmic ocean. Laniakea contains about 100,000 galaxies. Think about that for a moment. Each of those galaxies contains billions or even trillions of stars. Each star might have planets. And all of this unimaginable collection of matter and light and potential, is just one supercluster among many. The Laniakea Supercluster spans about 520 million light-years across. That's 5,200 times larger than the Milky Way. If the Milky Way were the size of a coin, Laniakea would be larger than a football field. Our entire galaxy, with all its stars and planets and wonders, is just a tiny speck within this colossal structure. Laniakea isn't evenly filled with galaxies. Instead, the galaxies are arranged in long filaments and sheets, like a cosmic web. Between these filaments are vast voids, regions of space that contain almost nothing. These voids are so empty that if you were floating in one, you might not see a single galaxy in any direction. It's emptiness on a scale that's hard to comprehend. The Milky Way sits on the outskirts of Laniakea, near the edge of the supercluster. We're not near the center or in any particularly special location. We're just out here, in a relatively quiet region, going about our slow orbit within the local group. And the local group itself is a minor feature within Laniakea, barely noticeable compared to some of the larger galaxy clusters. One of the largest structures within Laniakea is the Virgo cluster. This is a massive collection of galaxies located about 54 million light-years from us. The Virgo cluster contains over 1,500 galaxies, including some truly giant elliptical galaxies that dwarf the Milky Way. The Virgo cluster is so large and so massive that its gravity affects the motion of the entire local group. We're being pulled toward it, slowly drifting in its direction. Another major feature of Laniakea is the Great Attractor. This is a region of space with an enormous gravitational pull. For decades, astronomers noticed that galaxies in our part of the universe, including the Milky Way, were all moving toward the same point. They called this point the Great Attractor. It turns out the Great Attractor is a dense concentration of mass within Laniakea, pulling everything around it inward. The existence of superclusters like Laniakea was only confirmed relatively recently. For a long time, astronomers knew galaxies clustered together, but they didn't realize just how large those clusters could be. It wasn't until we developed better telescopes and more sophisticated ways of mapping the universe that we started to see the full picture. To map Laniakea, scientists studied the motion of galaxies. They looked at which direction each galaxy was moving and how fast. By analyzing these motions, they could see the invisible threads of gravity connecting everything together. It's like mapping the currents in an ocean by watching how the water flows. You can't see the currents directly, but you can see their effects. What they discovered was stunning. Laniakea isn't just a random collection of galaxies. It's a gravitationally bound system with a definite structure. Galaxies flow along specific paths, pulled by gravity into streams that converge toward the center of the supercluster. It's a slow, cosmic river carrying galaxies through space over billions of years. The Milky Way is part of this flow. We're being pulled along by the combined gravity of everything around us. In a sense, we're adrift in a current, moving through space along with countless other galaxies. Our motion is determined by the distribution of matter throughout Laniakea. We're not in control of where we're going, we're just along for the ride. When you think about it, the idea of a supercluster is almost too large to grasp. It's not just a collection of galaxies, it's a collection of galaxy groups, each of which contains multiple galaxies, each of which contains billions of stars. The scale is staggering. If you tried to count all the stars in Laniakea, even at a rate of 1 star per second, it would take trillions of years to finish. And yet, Laniakea is not unique. It's just one supercluster among many. Astronomers have identified numerous other superclusters scattered throughout the observable universe. Each one is similar in size and structure to Laniakea. Each one contains hundreds of thousands of galaxies, and each one is separated from the others by vast voids of empty space. These superclusters are the largest structures in the universe that are held together by gravity. Beyond the scale of superclusters, gravity becomes too weak to bind things together. Instead, the expansion of the universe takes over, pushing things apart faster than gravity can pull them together. This brings us to an important point. The universe is expanding. Space itself is stretching, causing galaxies and superclusters to move away from each other. The farther apart two objects are, the faster they appear to be moving away from each other. This expansion was discovered about a century ago and revolutionized our understanding of the cosmos. Within Laniakea, gravity is strong enough to hold things together despite the expansion. The galaxies within the supercluster are gravitationally bound, so they'll never drift apart. But Laniakea as a whole is moving away from other superclusters. Over time, the distances between superclusters will grow. Eventually, billions of years in the future, the voids between them will become so large that light from one supercluster will no longer be able to reach another. The universe will become a lonelier place. But we're getting ahead of ourselves. Right now, in the present, Laniakea is a vibrant, dynamic structure filled with galaxies. And somewhere within it, in a small galaxy group on the outskirts, is the Milky Way. That's us. That's home. A tiny, almost invisible part of something unimaginably vast. When we zoom out to the scale of Laniakea, the Milky Way essentially disappears. You'd need to know exactly where to look to find it. It's like trying to spot a single grain of sand on a beach. The galaxy that seemed so large and important when we started our journey now seems insignificant. It's humbling, it's awe-inspiring. And it's not even close to the full picture, because as vast as Laniakea is, it's still just one small piece of the observable universe. There are countless other superclusters out there, each one as large and complex as Laniakea. And all of them together, all the superclusters and all the galaxies, and all the stars, they're part of something even bigger, something that stretches the limits of what we can see and what we can understand. The cosmic web extends far beyond Laniakea. Filaments of galaxies stretch across hundreds of millions of light years, connecting superclusters to each other like threads in a vast tapestry. The voids between them are equally impressive, empty spaces larger than entire superclusters. This pattern of filaments and voids is the largest structure in the universe, a pattern that emerges from the way matter clumped together in the early universe. The formation of the cosmic web began shortly after the Big Bang. In the very early universe, matter was distributed almost uniformly, but there were tiny variations in density, small regions where matter was slightly more concentrated than average. These variations were incredibly small, just 1 part in 100,000, but they were enough. As the universe expanded, gravity amplified these tiny variations. Regions that were slightly denser attracted more matter, becoming even denser. Regions that were slightly less dense lost matter, becoming emptier. Over hundreds of millions of years, this process created the structure we see today. Dense regions became the filaments and clusters. Less dense regions became the voids. The cosmic microwave background, the afterglow of the Big Bang, still carries imprints of those original variations. Astronomers can see them as tiny temperature fluctuations across the sky. These fluctuations are like the seeds from which all cosmic structure grew. From such humble beginnings, galaxies, clusters, and superclusters eventually emerged. The filaments that make up the cosmic web are not simple lines. They're complex structures with their own internal patterns. Galaxies within filaments are often arranged in smaller chains and sheets. Some filaments are thick and dense, packed with galaxies. Others are thin and sparse, barely distinguishable from the surrounding voids. The filaments intersect at nodes, dense regions where multiple filaments meet. These nodes often contain large galaxy clusters. The voids, despite being called empty, aren't completely empty. They contain some galaxies, though far fewer than in the filaments. Void galaxies are typically small and isolated, separated from their neighbors by tens of millions of light years. Living in a void galaxy would offer a very different view of the universe. The night sky would be remarkably dark, with only a few faint smudges visible where nearby galaxies lie. Some voids are truly immense. The Bota's void, also known as the Great Nothing, is about 330 million light-years across. When it was discovered, astronomers were shocked to find such a large region containing so few galaxies. It seemed to contradict the idea that matter should be relatively evenly distributed. But the void fits perfectly into our understanding of the cosmic web. It's simply one of the larger empty spaces between the filaments. The motion of galaxies throughout the cosmic web follows the underlying distribution of mass, both visible and dark. Galaxies flow along the filaments, pulled by gravity toward the densest regions. This creates a pattern of motion that mirrors the web itself. By mapping these motions, astronomers can trace the structure of the web, even in regions where galaxies are too faint or distant to see clearly. Laniakea is part of this larger web, one node among many. The supercluster connects to neighboring superclusters through thin bridges of galaxies. These bridges are less dense than the main body of each supercluster, but they're there, linking structures across vast distances. The cosmic web is truly connected, a network spanning the entire observable universe. Within Laniakea, the distribution of galaxies is not random. Galaxies cluster together in groups and larger clusters, and these clusters are arranged in chains and sheets. The Virgo cluster, the largest structure in Laniakea, sits near the center of the supercluster. Its enormous mass influences the motion of all surrounding galaxies, including our own local group. The mass of Laniakea is dominated by dark matter, just like in smaller structures. For every kilogram of normal matter, there are about 5 kilograms of dark matter. This invisible component provides most of the gravitational pull holding the supercluster together. Without dark matter, Laniakea would fly apart, unable to maintain its structure against the expansion of the universe. The concept of a supercluster is relatively recent in astronomy. For most of the 20th century, astronomers thought galaxy clusters were the largest structures. They knew clusters were often found near other clusters, but they didn't realize these associations were themselves organized into larger systems. It wasn't until the 1980s, when astronomers completed large-scale surveys of galaxy positions, that the full extent of superclusters became clear. Even more recently, astronomers have recognized that superclusters aren't isolated. They're parts of an even larger structure, the cosmic web. This realization has transformed our understanding of the universe. We now see it not as a random scattering of galaxies, but as an organized network with structure at every scale, from small groups to giant superclusters to the web itself. Laniakea's name was chosen carefully. In 2014, when astronomers at the University of Hawaii published their work defining the supercluster, they wanted a name that captured its immense scale. Laniakea, meaning immeasurable heaven in Hawaiian, seemed perfect. It acknowledges both the vastness of the structure and the Hawaiian contribution to astronomy, with many of the world's most powerful telescopes located on Mauna Kea. The process of defining Laniakea was complex. Astronomers had to measure the positions and velocities of tens of thousands of galaxies. They used these measurements to map the gravitational influence holding the supercluster together. The boundary of Laniakea is not arbitrary. It's defined by the point where galaxies' motions change from being dominated by Laniakea's gravity to being dominated by the gravity of neighboring superclusters. This boundary is called a basin of attraction. Just as water in a valley flows toward the lowest point, galaxies within Laniakea flow toward the center of the supercluster. The boundary marks the edge of this flow, the point where galaxies start flowing toward a different center. It's like the continental divide in geography, except it's three-dimensional and extends across 520 million light-years. Adjacent to Laniakea are other superclusters with their own basins of attraction. The Perseus-Pisces supercluster lies in one direction, the Shapley Supercluster in another, and the Pavo-Indus Supercluster in a third. Each has its own center of mass, its own pattern of galaxy motions, its own identity. Together they form part of the larger cosmic web. The Shapley Supercluster deserves special mention. It's one of the most massive structures in the nearby universe, containing thousands of galaxies in a dense concentration about 650 million light-years away. The Shapley Supercluster's immense gravity pulls on Laniakea and neighboring superclusters, contributing to large-scale flows of galaxies through space. Some astronomers have proposed that Laniakea and the Shapley Supercluster might themselves be part of an even larger structure, though this is still debated. The Great Attractor, which we mentioned earlier, is actually not a single object. It's a region containing several massive galaxy clusters. The Norma cluster is one of them, a rich cluster located in a direction where dust from our own galaxy makes observation difficult. For years, astronomers knew something massive was there because they could see its gravitational effects, but they couldn't see it directly because of the intervening dust. The motion toward the Great Attractor is complex. It's not simply a matter of everything falling toward one point. There are multiple attractors, multiple concentrations of mass-pulling galaxies. In various directions, the overall motion is the result of all these gravitational influences combined. It's like water flowing downhill in a complex landscape with multiple valleys and ridges. Studying large-scale structure like Laniakea helps astronomers understand the evolution of the universe. The pattern of matter we see today is the result of billions of years of gravitational evolution, starting from those tiny variations in the early universe. By comparing observations to computer simulations, astronomers can test their theories about how structure forms and evolves. These simulations are remarkable achievements. Using supercomputers, astronomers can simulate the evolution of billions of particles representing dark matter and gas. They can start with conditions matching the early universe and run the simulation forward in time, watching as structure emerges. The best simulations produce results that closely match what we observe, giving us confidence that we understand the basic processes at work. From these simulations, we've learned that structure forms hierarchically. Small things form first, then merge to create larger things, which merge again to create even larger things. This process continues across all scales. Small dark matter halos merge to form galaxy-scale halos. Galaxies merge to form groups. Groups merge to form clusters, and clusters are organized into superclusters within the cosmic web. This hierarchical formation is still happening. The universe is still evolving, still building larger structures from smaller ones. Laniakea is not a finished product. It's still growing, still accumulating mass, still evolving as galaxies flow along the filaments toward the densest regions. In the distant future, assuming the universe continues to expand as it has been, this process will slow down and eventually stop as the expansion carries. Structures too far apart for them to interact. The study of Laniakea and other superclusters also sheds light on dark energy, the mysterious force causing the expansion of the universe to accelerate. Dark energy opposes gravity on the largest scales. While gravity tries to pull structures together, dark energy tries to push everything apart. The balance between these forces determines the fate of cosmic structure. Within Laniakea, gravity wins. The supercluster is gravitationally bound, meaning its internal gravity is strong enough to overcome the expansion. Galaxies within Laniakea will continue to interact and merge, eventually forming fewer, larger galaxies. But on scales larger than superclusters, dark energy dominates. The space between superclusters is expanding, carrying them farther apart, and this expansion is accelerating. This means that Laniakea, like all superclusters, is becoming increasingly isolated. The neighboring superclusters that are currently visible will eventually be carried beyond our cosmic horizon by the expansion. In the far future, an astronomer in Laniakea might look out and see nothing but darkness in all directions, with only the galaxies of Laniakea itself visible. The universe will appear much smaller than it does now, even though it's actually larger. But that's billions of years in the future. For now, Laniakea sits embedded in a rich cosmic web, surrounded by other superclusters, connected by filaments, separated by voids. It's a dynamic, evolving structure, part of a universe that's still unfolding its grand design. When the universe was young, tiny variations in density caused matter to gather in certain regions. Over billions of years, these regions grew, pulling in more matter, forming the galaxies and clusters we see today. The places where matter gathered became the filaments. The places it avoided became the voids. This process created the cosmic web, a structure that defines the layout of the entire universe. Laniakea is part of this web, one node in a vast network. And that network extends as far as we can see, filling the entire observable universe. But what exactly is the observable universe, and how much bigger might the true universe be? That's what we'll explore next, so let's keep going. Let's take the next step outward and see the observable universe in its entirety. We've zoomed out past our galaxy, past the local group, past the Laniakea Supercluster. Now we're going to pull back even further and see the observable universe. This is the term for everything we can possibly see, the entire volume of space from which light has had time to reach us. The observable universe is enormous. It's a sphere centered on Earth, extending about 46.5 billion light years in every direction. That makes the observable universe about 93 billion light years across. To put that in perspective, Laniakea, which seems so vast, is only about 520 million light years wide. The observable universe is nearly 200 times larger. You might wonder why the observable universe is so much larger than you'd expect. After all, the universe is about 13.8 billion years old. Shouldn't light have only traveled 13.8 billion light years in that time? The answer has to do with the expansion of the universe. While light has been traveling toward us, the space through which it's traveling has been stretching. This means objects that emitted light long ago have since moved much farther away. So even though the light itself is 13.8 billion years old, the objects that emitted it are now much more than 13.8 billion light years away. Within the observable universe, there are an estimated 2 trillion galaxies. That's 2,000 galaxies. Each one contains billions or trillions of stars. Each star might have planets. The total number of stars in the observable universe is estimated to be around 1 septillion. That's a 1 followed by 24 zeros. It's more stars than grains of sand on all the beaches on Earth. When we look at the observable universe, we're not seeing it as it is now. We're seeing it as it was in the past. Light takes time to travel, so when we look at distant objects, we're seeing them as they were when the light left them. When we look at a galaxy 100 million light years away, we're seeing it as it was 100 million years ago. When we look at the most distant galaxies, we're seeing them as they were more than 13 billion years ago, not long after the Big Bang. The most distant light we can see is the cosmic microwave background. This is the afterglow of the Big Bang itself, light that was emitted when the universe was only 380,000 years old. At that time, the universe was hot and dense, filled with a glowing plasma. As the universe expanded and cooled, that plasma became transparent, and light was able to travel freely through space. That light has been traveling ever since, stretched by the expansion of the universe into microwave wavelengths. Today, we can detect it with sensitive instruments. It fills the entire sky, a faint glow left over from the birth of the universe. The cosmic microwave background marks the edge of the observable universe. We can't see anything beyond it because the universe was opaque before that point. Light couldn't travel freely, so there's no light from earlier times for us to detect. In a sense, the cosmic microwave background is like a wall. We can't see past it, not because there's nothing there, but because the light from earlier times can't reach us. When astronomers map the observable universe, they see a cosmic web similar to what we saw in Laniakea, but on a much larger scale. Galaxies and superclusters are arranged in long filaments separated by vast voids. These filaments stretch across hundreds of millions of light years, forming a web-like pattern. It's the largest structure in the universe, a pattern that emerges from the way matter clumped together in the early universe. The voids between the filaments are the emptiest places in the universe. They contain very few galaxies, and those galaxies are spread incredibly far apart. If you were in the middle of a void, the sky would be almost completely dark. You might see a handful of faint, distant galaxies, but that's it. The nearest galaxy could be tens of millions of light years away. It would be a lonely, isolated place. The filaments, on the other hand, are where most of the action happens. This is where galaxies cluster together, where stars are born, where black holes grow, where all the interesting cosmic events take place. The filaments are like cosmic highways, dense with matter and energy, while the voids are like vast deserts, nearly empty and silent. The observable universe contains everything we can ever hope to study directly. Everything beyond it is forever out of reach, at least with current technology. Because space is expanding, distant objects are moving away from us faster than the speed of light. This might sound like it violates the rules of physics, but it doesn't. The objects themselves aren't moving through space faster than light. Instead, the space between us and them is expanding. It's a subtle but important distinction. As the universe continues to expand, more and more galaxies will cross a boundary called the cosmic horizon. Once they cross this boundary, their light will never be able to reach us, no matter how long we wait. The observable universe is shrinking in a sense. Not physically, but in terms of what we'll be able to see in the future. Distant galaxies are disappearing from view, one by one, as the expansion carries them beyond our reach. But for now, in the present, the observable universe is filled with wonders. It contains every galaxy we've ever seen, every star we've ever studied, every planet we've ever discovered. It contains all the matter and energy we know about, from the smallest particles to the largest superclusters. It's the sum total of everything we can observe and measure. And within that vast expanse, the Milky Way is almost invisible. If you were to create a map of the entire observable universe, our galaxy would be a single pixel. You'd need to zoom in significantly just to see Laniakea, and you'd need to zoom in even more to see the local group. The Milky Way, with all its hundreds of billions of stars, would be too small to notice unless you knew exactly where to look. This is where the true scale of the universe starts to sink in. The Milky Way, which seemed so impossibly large at the start of our journey, is nothing compared to the observable universe. It's a speck, a grain of sand in a vast desert. And yet, it's our home. It's where we come from. It's where all of human history has taken place. The observable universe represents the limit of what we can see with telescopes and instruments. But it's not the limit of what exists. The universe doesn't end at the edge of what we can observe. It's just that light from beyond that boundary hasn't had time to reach us yet. So what lies beyond? How much bigger? How much might the true universe be? These are questions that push the boundaries of science and philosophy. The concept of the observable universe is tied to the speed of light and the age of the universe. Light travels fast, but not infinitely fast. It has a speed limit, about 186,000 miles per second, or about 300,000 kilometers per second. This seems incredibly fast by human standards, and it is. But the universe is so large that even at this speed, it takes light a very long time to travel across it. The universe is approximately 13.8 billion years old. That means light has had 13.8 billion years to travel since the Big Bang. You might think this means we can see objects up to 13.8 billion light years away, but it's more complicated than that because the universe has been Expanding the whole time, objects that emitted light long ago have since moved much farther away. By the time their light reaches us, they're much more distant than the light's travel time would suggest. Taking into account the expansion of space, the edge of the observable universe is about 46.5 billion light-years away in every direction. This gives the observable universe a total diameter of about 93 billion light-years. It's a sphere centered on Earth, not because Earth is special, but simply because that's where we're observing from. An observer in another galaxy would have their own observable universe, a sphere centered on their location, which would overlap with ours but extend in different directions. The number of galaxies in the observable universe is staggering. The latest estimates, based on observations from the Hubble Space Telescope and other instruments, suggest there are about 2 trillion galaxies. That's 2,000 galaxies. Each one contains anywhere from a few million to several trillion stars. If we try to count all the stars in the observable universe, we get a number around 1 septillion, or 10 to the power of 24. That's a 1 followed by 24 zeros. To put that in perspective, there are roughly 10 to the power of 23 stars in the observable universe. There are estimated to be about 7 times 10 to the power of 18 grains of sand on all of Earth's beaches. That means there are more stars in the universe than grains of sand on Earth by a factor of several thousand. For every single grain of sand on every beach, there are thousands of stars shining somewhere in the cosmos. The distribution of those 2 trillion galaxies is not random. As we've seen with Laniakea, galaxies are organized into groups, clusters, and superclusters, all arranged in the cosmic web of filaments and voids. This pattern extends throughout the entire observable universe. No matter which direction we look, we see the same basic structure: galaxies clustered along filaments with vast voids in between. This uniformity is remarkable. The universe looks roughly the same in all directions, at least on large scales. This is called the cosmological principle, and it's one of the foundations of modern cosmology. The principle states that the universe is homogeneous and isotropic, meaning it has the same properties everywhere and looks the same in all directions. Of course, on small scales, there are variations. Galaxies cluster in some regions and avoid others. But when you zoom out far enough, averaging over large volumes, the universe appears uniform. This uniformity extends to the cosmic microwave background as well. When astronomers map the CMB across the entire sky, they find that it has almost exactly the same temperature in every direction. There are tiny variations, less than 1 part in 100,000, but overall, it's remarkably uniform. This tells us that the early universe was very smooth, with only tiny density fluctuations that later grew into the structure we see today. The most distant objects we can see are not galaxies, but the cosmic microwave background itself. This radiation comes from a time when the universe was only 380,000 years old. Before that time, the universe was filled with hot plasma that was opaque to light. Photons couldn't travel far before being absorbed and re-emitted by free electrons, but when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, the plasma became transparent. Light could suddenly travel freely through space. The CMB is this light, now redshifted by the expansion of the universe from visible wavelengths into microwaves. The CMB provides a snapshot of the universe at that early time. By studying its properties, astronomers can learn about the conditions in the early universe, test theories of cosmic inflation, and measure key parameters like the age and composition of the universe. It's one of the most important sources of information we have about cosmology. Beyond the CMB, we can't see anything directly. The universe before 380,000 years was opaque, but we can detect traces of that earlier era in other ways. Gravitational waves, ripples in space-time itself, can carry information from even earlier times. The universe was never opaque to gravitational waves, so they can reach us from the very earliest moments of cosmic history. Detecting these primordial gravitational waves is one of the major goals of modern physics. The expansion of the universe has profound implications for what we can see. Not only does it mean that distant objects have moved farther away since they emitted their light, but it also means that light from the most distant objects is severely redshifted. Redshift occurs because the wavelengths of light are stretched as space expands. The farther away something is, the faster it's moving away from us due to expansion, and the more its light is redshifted. The most distant galaxies we've observed have redshifts greater than 10. This means their light has been stretched to more than 10 times its original wavelength. Light that was emitted in the ultraviolet or visible range has been shifted all the way into the infrared. That's why infrared telescopes like the James Webb Space Telescope are so important for studying the early universe. They can see galaxies that are invisible to optical telescopes because their light has been redshifted too far. As telescopes improve, astronomers keep pushing back the distance record, finding ever more distant and therefore ever younger galaxies. Each discovery gives us a glimpse of the universe at an earlier stage in its evolution. We can see how galaxies have changed over cosmic time, how they looked when they were young compared to how they look today. We can trace the history of star formation, the buildup of elements, the growth of supermassive black holes, all by looking deeper and deeper into space and therefore further and further back in time. There's a limit to this process, though. Eventually, we reach the era before the first stars formed, when the universe was dark and filled only with neutral hydrogen gas. This period, called the Cosmic Dark Ages, lasted for several 100 million years. No stars existed yet, so there was no light from galaxies to see. Eventually, the first stars ignited, ending the Dark Ages and beginning the era of cosmic dawn. Finding and studying these first stars and galaxies is one of the most exciting frontiers in astronomy. Even beyond the cosmic dark ages, there's the era of recombination when the CMB was emitted, and beyond that, the earlier era when the universe was too hot for neutral atoms to exist. Going even further back, there was the era of inflation, a period of extremely rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. Inflation is thought to be responsible for the uniformity of the CMB and the large-scale structure of the universe. And before inflation, that's where our understanding breaks down. We don't know what happened in the very first moment, at the exact instant of the Big Bang. Our physical theories break down at that point. We can't describe what happens when matter reaches infinite density and the temperature is infinite. We need a theory of quantum gravity to understand that regime, and we don't have one yet. But within the observable universe, from the CMB to the present day, we have a remarkably detailed understanding of cosmic history. We know how the universe has evolved, how structure has grown, how galaxies have formed and changed. We can see the results all around us in the 2 trillion galaxies filling the observable universe. The observable universe also has a horizon, a boundary beyond which we can never see, no matter how long we wait. This isn't because there's nothing there, but because the expansion of space carries those regions away faster than light can travel. Objects beyond the cosmic horizon are moving away from us faster than the speed of light, not because they're moving through space that fast, but because the space between us and them is expanding that rapidly. This might seem to violate Einstein's rule that nothing can move faster than light, but it doesn't. The speed limit applies to motion through space, not to the expansion of space itself. Space can expand at any rate. Objects can be carried apart by expansion faster than light could travel between them, and this doesn't break any laws of physics. As time goes on, more and more galaxies cross this horizon and disappear from view. The observable universe is, in a sense, shrinking, even though the universe as a whole is expanding. Galaxies that we can see today will eventually be carried beyond our horizon. Billions of years in the future, observers in our galaxy will see fewer distant galaxies than we do. The universe will appear emptier, lonelier, even though it's actually larger. This is one of the strange consequences of cosmic acceleration. Not only is the universe expanding, but the expansion is speeding up. This was discovered in the late 1990s by observing distant supernovas and measuring their distances and redshifts. The discovery that expansion is accelerating came as a complete surprise and earned the discoverers the Nobel Prize. Nobody knows what's causing this acceleration. It's attributed to dark energy, but dark energy is really just a name for our ignorance. We don't know what it is or how it works. Despite these mysteries, we can say with confidence that the observable universe is immense, filled with galaxies, structured in a cosmic web, and evolving according to physical laws we mostly understand. From the CMB to the nearest galaxies, from the voids to the filaments, from the dark ages to the present, It's a majestic, awe-inspiring realm. And it's the stage on which all of cosmic history has unfolded, including the emergence of life on at least one small planet orbiting one ordinary star. Some scientists believe the universe might be infinite, extending forever in all directions. If that's true, then the observable universe is just an infinitely small fraction of what exists. Others think the universe might be finite but unbounded, like the surface of a sphere. And some believe it might be part of a multiverse, one universe among countless others. These are deep questions, and we don't have definite answers yet. The question of whether the universe is finite or infinite is one of the most profound in all of science. It's not just about size, it's about the fundamental nature of reality itself. Is space finite, bounded, with an edge somewhere? Or does it go on forever, with no boundary, no edge, nothing beyond? Current observations suggest that the universe is flat or very close to flat. In cosmology, flat doesn't mean two-dimensional. It means that the geometry of space follows the rules of Euclidean geometry, the geometry you learned in school. Parallel lines never meet. The angles of a triangle add up to 180 degrees. A flat universe can be infinite, extending forever in all directions like an endless plane. A curved universe would be different. If space has positive curvature, like the surface of a sphere, then the universe would be finite. If you traveled in a straight line, you'd eventually come back to where you started, just like traveling around the Earth's surface. A universe with negative curvature, like a saddle, would be infinite, but would have different geometric properties than a flat universe. Measurements of the cosmic microwave background allow astronomers to determine the curvature of space with remarkable precision. The current best measurements indicate that the universe is flat to within less than 1%. This suggests, though it doesn't prove, that the universe might be infinite. If it has even the slightest curvature, it's so small that the universe would be much, much larger than the observable portion. If the universe is infinite, the implications are startling. In an infinite universe with a finite number of particle configurations in any given volume, everything that can happen will happen infinitely many times. There would be infinitely many regions identical to our observable universe. There would be infinitely many copies of you, living identical lives, making identical choices, reading these identical words right now. But there would also be regions that are almost but not quite identical. Regions where your life went slightly differently, where you made different choices, where history unfolded along different paths, and regions that are completely different with different galaxies, different laws of physics perhaps, or even no galaxies at all. This is called the infinite duplication problem, or sometimes the Boltzmann brain problem. In an infinite universe, even incredibly unlikely events must occur somewhere. Random quantum fluctuations could assemble brains from the vacuum, complete with false memories of lives never lived. These Boltzmann brains would vastly outnumber real brains that evolved naturally, simply because there are so many more ways for random fluctuations to create brains than for evolution to produce them. Physicists don't like this conclusion. It seems absurd, but it follows logically from an infinite universe, combined with our understanding of quantum mechanics and thermodynamics. Resolving this problem is one of the challenges for modern cosmology. Some think it means the universe can't be truly infinite. Others think it means we need to revise our understanding of probability in an infinite cosmos. Another possibility is the multiverse. In some versions of inflationary cosmology, our observable universe is just one bubble in an eternally inflating space. Inflation never stops everywhere. It stops in some regions, creating bubble universes like ours, but continues in other regions, creating new bubble universes constantly. This process goes on forever, generating an infinite number of bubble universes, each with potentially different properties. In the multiverse scenario, our observable universe is not just one region in a vast space. It's one entire universe in a collection of universes. The other universes might have different physical constants, different laws of physics, even different numbers of dimensions. We could never visit or observe these other universes because they're separated from us by regions of ongoing inflation. They're causally disconnected, forever beyond our reach. The multiverse is controversial. Some physicists embrace it as a natural consequence of inflation. Others reject it as untestable and therefore unscientific. If we can never observe or interact with other universes, can we really say they exist? Or is the multiverse just a mathematical possibility that happens to arise in our theories but has no physical reality? These are philosophical questions as much as scientific ones. They touch on the nature of existence, the limits of knowledge, and what it means for something to be real. Science works best when theories can be tested against observations. But when theories make predictions about regions we can never observe, how do we test them? Some physicists argue that we can test multiverse theories indirectly. If the multiverse exists and has certain properties, it might leave subtle imprints on the cosmic microwave, background, or affect the probability distributions of physical constants in our universe. Looking for these indirect signatures is an active area of research. Others argue that the multiverse is a beautiful mathematical idea, but not a physical theory. They seek alternatives to inflation that don't produce multiverses, or they look for ways to make inflation end globally rather than continuing forever in some regions. The debate continues with passionate arguments on both sides. Setting aside the multiverse, even if we focus just on our own universe, the question of its total size remains open. Conservative estimates based on the flatness of space and the duration of inflation suggest the universe is at least hundreds of times larger than the observable portion. But it could be much larger than that. It could be millions or billions or trillions of times larger, or it could be infinite. If the universe is even just 1,000 times larger than what we can observe, it contains regions that are completely disconnected from us. Regions we can never see or influence, and that can never see or influence us. These regions are as real as anything in the observable universe, filled with their own galaxies and stars and possibly even life, but forever beyond our knowledge. The expansion of space means that regions currently just beyond our horizon are moving farther away. The boundary of the observable universe is not static. It's expanding as light from more distant regions reaches us. But the cosmic horizon, the boundary beyond which recession velocity exceeds the speed of light, is also moving. Objects just inside the horizon today will cross it in the future. The observable universe grows, but the reachable universe shrinks. In the far future, assuming dark energy remains constant, the observable universe will contain only the galaxies gravitationally bound to our local group. Everything else will have been carried beyond the horizon. Astronomers of that distant era, if any exist, will look out and see a dark, empty universe, with only a few nearby galaxies visible. They'll have no way of knowing that the universe was once filled with billions of galaxies, no way of knowing about the cosmic web, no way of understanding cosmic history. The evidence will have literally disappeared. This makes us fortunate to live in an era when we can still see the distant universe. We can observe the CMB, study distant galaxies, trace the cosmic web, and learn about the universe's history and structure. Future civilizations won't have this opportunity. In a sense, we're living in a golden age of cosmology, able to see farther and learn more than any future observers will be able to. The concept of the unobservable universe, the regions beyond what we can ever see, challenges our intuitions about reality. We're used to thinking that real means observable, that if we can't see something, it doesn't exist. But the universe doesn't care about our limitations. It exists whether we can see it or not. The galaxies beyond our horizon are just as real as the ones we can see. They just happen to be too far away for their light to reach us. This humility in the face of cosmic vastness is appropriate. We occupy a tiny corner of space in a brief moment of cosmic history. What we can see is just a fraction of what exists. What we know is just a fraction of what can be known, and yet we've learned so much. We've mapped the observable universe, traced its history, understood its structure, and glimpsed its fate. That's remarkable. The Milky Way, in this context of the possibly infinite universe, is unimaginably small. If the universe is infinite, our galaxy occupies exactly 0% of the total volume. It's infinitely small. Even if the universe is merely finite but vastly larger than the observable portion, the Milky Way is still a negligibly tiny speck. And within the Milky Way, our solar system is a tiny speck. Within the solar system, Earth is a tiny speck. And on Earth, each of us is a tiny speck. We're specks on a speck on a speck on a speck in a possibly infinite universe. It's humbling. It's awe-inspiring. It's beautiful. But here's the thing. The observable universe, as vast as it is, isn't the entire universe. It's just the part we can see. Beyond the edge of what we can observe, there's more. Possibly much, much more. And that's where things get truly mind-bending. The observable universe has a boundary, not because the universe ends there, but because light from beyond that boundary hasn't had time to reach us yet. But that doesn't mean there's nothing beyond it. In fact, there's every reason to think the universe extends far beyond what we can see. The question is, how far? And that's what we'll explore next. The observable universe is limited by light and time. We can only see as far as light has had time to travel since the Big Bang, but there's no reason to think the universe ends at that boundary. Most scientists believe the universe extends far beyond what we can observe. The question is, how far? Some models suggest the universe is infinite, not just very large, but truly infinite, stretching on forever in all directions. If that's true, then the observable universe is like a tiny bubble in an endless ocean. Everything we can see, all 2 trillion galaxies, all septillion stars, all of it would be just an infinitesimally small fraction of what exists. Imagine an island in an infinite ocean. That's the observable universe. The island has beaches and trees and rocks, all the features you'd expect. But beyond the shore, the ocean goes on forever. You can see the water near the island, but you can't see the water far away. It's too distant, beyond your horizon. That doesn't mean the ocean ends at your horizon. It just means you can't see beyond it. The universe is like that ocean, and the observable universe is like that island. If the universe is infinite, then everything that can happen has happened somewhere. There would be infinite copies of the Milky Way, infinite copies of Earth, infinite copies of you. It's a strange thought, but it follows logically from an infinite universe. In an infinite space, every possible arrangement of matter will occur, not just once, but infinitely many times. There would be regions of space identical to our own, where history played out exactly the same way. And there would be regions where things went differently, where minor variations led to completely different outcomes. Of course, we don't know for certain whether the universe is infinite. It might be finite but unbounded, like the surface of a sphere. If you walk in a straight line on a sphere, you'll eventually come back to where you started. The universe could be like that, curved in a way that makes it finite, but without any edges. If you traveled in a straight line through space, you'd eventually return to your starting point, having circumnavigated the entire universe. Another possibility is that the universe is finite and still expanding. In this scenario, the universe has a definite size, but that size is increasing over time. The space itself is stretching, carrying galaxies apart. Eventually, the universe might expand forever, growing larger and larger, becoming ever more empty and cold. Or it might stop expanding and start contracting, eventually collapsing back into itself in a big crunch, the opposite of the Big Bang. We don't know which of these scenarios is correct. We don't have enough data to say for certain what the shape and size of the universe are. What we do know is that the universe is much, much larger than the observable universe. Even conservative estimates suggest it's at least hundreds of times bigger, and if it's infinite, then the observable universe is nothing by comparison. Think about that for a moment. Everything we've discussed so far, from the Milky Way to the local group to Laniakea to the entire observable universe, all of it might be a tiny, insignificant speck in something incomprehensibly vast. The true universe could be so large that our entire observable region, with its 2 trillion galaxies, is just one tiny patch in an endless expanse. This is where the comparison from the video title reaches its climax. The Milky Way, compared to the infinite universe, is less than nothing. It's smaller than a single atom compared to the size of the entire Earth. No, even that doesn't capture it. An atom is at least something measurable. The Milky Way, in the context of an infinite universe, is infinitely small. It occupies 0% of the total volume. It's as close to nothing as you can get without actually being nothing. And yet, despite all this, the Milky Way matters. It matters because it's where we are. It's where life exists, at least the life we know about. It's where the atoms that make up your body were forged in ancient stars. It's where planets formed and evolved and gave rise to creatures capable of looking up at the sky and asking questions about the universe. The vastness of the universe doesn't diminish us. If anything, it makes us more remarkable. Against all odds, in this one small galaxy among trillions or infinite galaxies, conditions were right for life to emerge. That life evolved over billions of years, becoming more complex until eventually it produced beings capable of contemplating their own existence. That's not insignificant. That's extraordinary. When we think about the scale of the universe, it's easy to feel overwhelmed. It's easy to feel small and unimportant. But smallness isn't the same as insignificance. You are made of atoms that were forged in the hearts of stars. You are a way for the universe to know itself. Every thought you have, every feeling, every moment of awareness is the universe experiencing itself through you. The Milky Way may be tiny compared to the infinite universe, but it's also unique. It's the place where you exist. It's the place where all of human history has unfolded. It's the place where we first learned to look up at the stars and wonder what's out there. That makes it special, regardless of its size. So yes, our galaxy is incredibly small compared to the universe. It's a speck, a grain of sand, a single atom in an infinite ocean. But it's our speck, it's our grain of sand, and that makes all the difference. Let's bring this journey to a close by stepping back and taking in the full picture one more time. We started on Earth in our solar system, looking up at the Milky Way. Our galaxy seemed vast, and it is 100,000 light years across, containing hundreds of billions of stars. It's an almost incomprehensible scale. But then we zoomed out. We saw the local group, a collection of galaxies including our own. The Milky Way became one member among many. We zoomed out further and saw Laniakea, a supercluster containing 100,000 galaxies. The Milky Way became a tiny speck. We zoomed out again and saw the observable universe with its 2 trillion galaxies. The Milky Way virtually disappeared, and finally we considered the true universe, possibly infinite, extending far beyond what we can ever hope to see. In that context, the Milky Way is nothing. It's infinitely small. If you picked a random point in an infinite universe, the chances of landing anywhere near the Milky Way would be exactly 0. This is the comparison we set out to explore. How tiny is our galaxy compared to the infinite universe? The answer is incomprehensibly tiny, smaller than we have words to describe. And yet this isn't a depressing thought, it's a beautiful one. Because in all that vastness, in all that infinite space, this one tiny galaxy is where you are. It's where the atoms that make up your body were created. It's where your story is unfolding. The journey we've taken tonight has been one of perspective. We started with something familiar, the Milky Way, our home galaxy. It seemed enormous, and by human standards it is. But then we stepped back and back and back again, each time revealing a larger structure. With each step, the Milky Way became smaller in relation to what surrounded it. At the scale of the local group, our galaxy was still significant, one of the largest members. But at the scale of Laniakea, it became just one small dot among thousands. At the scale of the observable universe, it virtually disappeared, requiring precise coordinates to locate. And at the scale of the possibly infinite true universe, it became mathematically nothing, occupying 0% of the total. This progression mirrors the historical progression of human understanding. For most of history, humans thought Earth was the center of everything. The sun, moon, planets, and stars all revolved around us. We were central, important, special. Then Copernicus and Galileo showed that Earth orbits the sun, not the other way around. We were displaced from the center. Later, astronomers realized the sun was just one star among billions in the Milky Way, and not even a particularly special one. We were displaced again. Then Edwin Hubble discovered that the Milky Way was just one galaxy among countless others, another displacement. And now we know that even our galaxy, vast as it is a negligible speck in a possibly infinite cosmos. We've been thoroughly displaced from any position of cosmic centrality. But this displacement hasn't diminished us, it's done the opposite. Each expansion of our cosmic perspective has enriched our understanding, deepened our appreciation for the universe, and made the existence of life more remarkable. Against the backdrop of cosmic vastness, the emergence of conscious beings capable of contemplating the cosmos seems even more extraordinary. Life, as far as we know, is rare. We haven't found it anywhere else yet, though we're still looking. Even if life exists on millions or billions of other worlds, which seems likely, it still represents a tiny fraction of planets, which themselves are a tiny fraction of stellar systems, which are a tiny fraction of galaxies, which are a tiny fraction of the universe. Conscious life capable of building civilizations and studying the cosmos might be even rarer. We don't know. We're still searching for signs of other technological civilizations, listening for radio signals, looking for artifacts, examining exoplanet atmospheres for biomarkers. So far, we've found nothing. We might be alone in the observable universe, or there might be millions of other civilizations out there. We simply don't know yet. Either way, we're remarkable. The atoms that make up your body were forged in stellar furnaces billions of years ago. When massive stars died in supernova explosions, they scattered these elements into space. The elements drifted through the galaxy for millions of years, eventually becoming part of a cloud of gas and dust. That cloud collapsed to form our sun and its planets. Earth coalesced from the dust, a ball of rock rich in heavy elements from ancient dead stars. On this rocky world, something astonishing happened. The elements combined in complex ways. Molecules formed, self-replicating molecules, primitive life. Over billions of years, evolution shaped this life, making it more complex, more diverse, more capable. Eventually, life developed nervous systems, brains, consciousness. It became aware of itself. It began to ask questions. You are the product of this incredible journey. You are 13.8 billion years of cosmic evolution made manifest. You are hydrogen that learned to think, stardust that became conscious. When you look up at the night sky, you're not separate from what you see. You're part of it. The universe is looking at itself through your eyes. This unity with the cosmos is profound. We talk about the universe as if it's something separate, something out there. But it's not. It's here. It's you. Every atom in your body, every thought in your mind, every feeling you experience, all of it is the universe in action. You're not an observer of the cosmos, you're a participant, a part of the cosmic story that's been unfolding since the Big Bang. The smallness of the Milky Way and your smallness within it doesn't make you insignificant, it makes you special. In a universe so vast that our galaxy is virtually nothing, the fact that consciousness arose in this particular galaxy on this particular planet is extraordinary. It might have happened elsewhere too. Probably has if the universe is large enough, but that doesn't diminish the wonder of it happening here. There's a concept in philosophy called the mediocrity principle. It says that Earth and humanity are not special, that we're typical of what exists throughout the universe. This principle has been useful in science, helping us overcome our bias toward thinking we're central or unique, but it can be taken too far. We might be typical in some ways, but in others we're utterly unique. There's only one Earth, only one history of life on Earth, only one human civilization. Even if there are millions of other civilizations in the universe, each one is unique. Each has its own history, its own path of development, its own perspective on the cosmos. We might not be alone, but we're still special. Our particular configuration of matter, our specific arrangement of atoms into living, thinking beings exists nowhere else exactly. So as we contemplate the vastness of space and our tiny place within it, let's not feel small or insignificant. Let's feel connected. Let's feel privileged to be alive in a time and place where we can look up at the stars, where we can build telescopes and spacecraft, where we can map the universe and understand its history. Let's feel grateful for the billions of years of cosmic evolution that led to this moment. The Milky Way might be infinitesimally small compared to the infinite universe, but it's infinitely precious because it's home. It's where we come from, where we live, where we'll stay for the foreseeable future. We're bound to this galaxy by more than just gravity. We're bound to it by history, by biology, by the deep connection between the atoms in our bodies and the atoms forged in the galaxy's stars. In contemplating cosmic scale, we find both humility and wonder. Humility because we're so small, so brief, so limited in what we can see and know. Wonder because despite these limitations, we've learned so much. We've traced our origins back to the Big Bang. We've mapped the structure of the observable universe. We've glimpsed the possibility of realms beyond our sight. That's the power of curiosity, intelligence, and the scientific method. As you settle into sleep tonight, imagine the vast spaces we've explored. Imagine the Milky Way spinning slowly through the darkness, its spiral arms glowing with young stars. Imagine the local group, scattered galaxies bound by invisible threads of gravity. Imagine Laniakea, that immeasurable heaven stretching across hundreds of millions of light years. Imagine the observable universe, filled with 2 trillion galaxies structured in a cosmic web of filaments and voids. And imagine beyond that, regions we'll never see, spaces too distant for their light to reach us, perhaps an infinite universe extending forever in all directions. All of it real, all of it wondrous, all of it part of the grand cosmic story. And you, sleeping peacefully on your small world, are part of that story too. You belong here. You're home. You are a part of the universe. You're not separate from it. The universe is not just something out there, distant and cold. It's here. It's you. Every breath you take, every thought you think, is the universe in motion. You are the cosmos experiencing itself, aware of itself, marveling at itself. That's profound. That's meaningful. So as you drift off to sleep tonight, remember this. You are small, yes, but you are not insignificant. You are connected to everything, from the smallest particle to the largest structure in existence. You are made of stardust. You are a child of the universe. And the universe, in all its infinite vastness, has given rise to you. That is something to find peace in. Thank you for joining me on this journey through space and scale. I hope it's given you a new perspective on our place in the cosmos. The Milky Way may be tiny compared to the infinite universe, but it's still our home. It's still where all of us together are experiencing this vast and mysterious reality. If you found this video relaxing and thought-provoking, I'd appreciate it if you'd like and subscribe. It helps others discover this content and allows me to keep creating these explorations of science and space. These journeys through the cosmos are meant to bring peace and perspective, to help you see your place in the grand scheme of existence. Feel free to leave a comment sharing your thoughts. What did this journey make you think about? How do you feel about our place in the universe? Your reflections matter, and I'd love to hear them. For now, rest well. Let the vastness of space be a comfort rather than a worry. You are exactly where you need to be. Good night and sleep well under the stars.